Okay, so this is the second part of week 4, and this is the part where I'm actually going to talk about the techniques. Part 1 talked about the background, very important to understand the concept of calculating distance, um, as well as the fact that we're working with unstructured data. So, but in this part, we actually get into doing the clustering. Okay. What are the basics of cluster analysis? Cluster analysis in data mining is working with unlabeled data. Very specifically, you don't have a target variable to label things here. And it's based on distance metrics. Okay. You would want to use cluster analysis when you have data that you sort of like don't understand the structure of. It's really sort of a beginning step, and you're looking for hidden patterns and underlying structure in the data. Remember that data mining is all about pattern finding. So literally the entire course is we're trying to figure out in data and try to look for patterns that may be of use to us, may be novel, that may lead us to further studies. So as a criteria for using cluster analysis, you have to have at least 2 attributes, aka variables, that are quantitative. It doesn't mean that, you can have 10 categorical variables. Usually you can't, I shouldn't say always, but I mean, if your categorical variables are binary, you can put them in and you can use that binary distance metric. It's a Jaccard distance. You can't do cluster analysis, at least I don't think so. I shouldn't say this because I think there are other techniques you can do. But cluster analysis based on distance needs to have 2 quantitative variables to measure distance on. And if at least one of them is continuous, you can use the Euclidean distance metric. But if you have all binary data, you must use that Jaccard metric. Okay. So when you have cluster data that you're in cluster, you want to pre-process and normalize as discussed in the last video. You can do the clustering on the normalized data, or you can also do it on principal components. Remember, the principal components are done on normalized data too, so you don't have to renormalize them. Just don't forget to do your principal components on normalized data. That was from the last week stuff on principal components. So we will typically do it directly on data for this course, but keep in mind that you can do it on the principal components as well. Okay. You don't have to use all the variables in your data when you're clustering. In fact, if your data is like all text data and stuff, like you wouldn't want to use like client address as a cluster variable. No. What you wouldn't want to use as cluster variables are things like the items they purchase, or like maybe like look for clusters of your customer types and look at the demographics and cluster those and see if you can find like groups of people like that. So go over your data dictionary if you have one. If you don't, use what you can based on your exploratory analysis. Try to understand the best variables to use. You can, I shouldn't say, you certainly can use all your variables. I mean, if you only have like 5 quantitative variables in a data set, sure, why not? But if you have like 100 variables, you might want to pick like 6 of them to use for your cluster analysis. Okay. And those would typically be things that are like informational, but you don't know the structure of, like customer traits. You might want to pick like gender and like age, and try to see like if you can group like your clients in certain ways to see that, like, look for like certain customer groups that you can target with different marketing strategies or something like that. I should also mention, this stuff is near and dear to me. My master's thesis work at UNH years and years ago, what I did is I clustered genes that expressed in DNA microarrays. I think I still have my master's presentation. I mean, in those days, hardly anybody did cluster analysis, but the reason I did cluster analysis for that is I was looking at the expression of hundreds of different genes, and you wanted to cluster the genes that express together, and those are like important biological pathways. So cluster analysis is actually a great technique for when you have novel data and you want to group it. But you don't have to throw every single variable in it. Something like an ID number, you'd never throw something like that. It has to be like, understand your data enough to throw in like a meaningful variable. Like, don't throw in like football jersey numbers unless for some reason there's something that you would want in that. Don't. Okay. Clustering data is grouped on similarity. Similarity means mathematical distance. The computation of similarity is that distance formula, which extends into n dimensions, so you can have as many variables as you want to throw in. And there are several other metrics. Typically we'll use Euclidean, but there are other metrics, including that one for binary data. Cluster analysis is highly exploratory, which is good because what do you do with data that you don't fully understand? You start with something like cluster analysis. Because unlike your sort of basic exploratory data analysis techniques that you can do on like one variable, cluster analysis you can work with and you're finding patterns with different variables, which you can't really do that with just by looking at basic graphs and basic statistics on each variable. So cluster analysis can be a lead to further types of analysis, but it is very often kind of like a nice first step. Okay. Potential uses of cluster analysis. Business uses, looking for buying patterns. Maybe you would want to cluster like what items people are buying together and try to see like, maybe stuff that you would want to bundle in like a bundle deal or something like that. The biological applications, stocks that behave in certain ways, like stocks that go up and down together, those would be clusters. There's a lot of uses of cluster analysis. And so this again is my wonderful art. Okay. So here we have, I didn't mean for these to be labels, but I labeled 3 of them blue and 2 of them, I think it's gray. But there's 2 different things going on here. So we have the blue cluster and the gray cluster. You can measure 2 different distances, by the way. Okay, and you're like, what? There's the distance within each cluster and the distance between each cluster. Okay, so group data such that data in a cluster will be like, what you want is for the data within the cluster, intercluster, you want the intercluster distance to be smaller than the intercluster, right? So you want these guys to be close and it to be further away from these guys. These guys are close to each other, but they're further away from these guys and these guys are close to each other. I don't know if that makes any sense, but that's the idea. Okay. So you want to minimize the intracluster distance and maximize the intercluster distance. Okay. Cool. There's 2 main cluster methodologies that we're going to study. There's one called hierarchical, which what hierarchical does is groups things all together so that they agglomerate, so everything becomes one big structured cluster. Whereas k-means, you have separate clusters. So this essentially is kind of like a big tree. And this one is separate little bubbles. Okay. I think there are other clustering methods, but I got to tell you, these 2 are really the clustering methods. Classification has a lot of methods, but clustering really, it's pretty much always k-means and hierarchical. Okay. So we're going to start with the hierarchical. Okay. A hierarchy is a structure of different levels. Okay. It begins at the level of the individual data point, and you repeatedly merge together, creating clusters as you go on. Hierarchical clustering is also called agglomerative. There is such a thing as divisive, but agglomerative is the one that is typically used. So don't confuse. Now, you haven't learned decision trees yet. You'll learn them next week, but don't confuse this with decision trees because they're not decision trees. Okay. So here is my illustration of hierarchical clustering. I don't know if these are the same points as before. I don't know. Anyway, so I have points A, B, C, D, E, F because this is very exciting. And I have X and Y values for these points. And then I plotted them. This is a little hard to see, but I color-coded them. I was kind of lazy and I didn't fix the slide up as probably I should have. I didn't know how to make these bubbles bigger. But in the bottom right corner, this is point A, B, C, D, E, and F. So this is an XY plot of this data. Okay. Initially, so hierarchical clustering starts with all 6 points are just individual clusters. Okay. Nothing is grouped yet. Then what we do is we calculate the distance matrix. Yeah, this is the same example as from part 1 in terms of so this is the distance matrix done in software, which the software made this automatically. I didn't make this. You're kidding. It's too nice. These are not standardized. Well, this one they don't have to be. That is actually a point in that this data is technically not standardized, but this is just toy data, so you get the idea. In other words, if this were real data, I'd want to be working on standardized data, but this is just made up numbers with no units. So, okay. So, what does it do first? Okay. The first thing it does is it finds the closest points, which the smallest distance is A to B and then C to D. So these two are relatively small distances. These are the only two that are below 2. So it creates clusters now. It clusters A and B, and it clusters C and D. E and F still remain separate because they're pretty far away. So the first step in hierarchical clustering is first everything's an individual point. I mean, everything starts as an individual point, and then you get clusters formed with the closest things. So now we have these as a cluster, and these as a cluster, and these two as just individual points as clusters. Okay. Next, okay, individual points distances come from the distance matrix. You also have to calculate the cluster-to-cluster distance. Okay. So there is such a thing now as not just the distance between the points. This is the distance between the points. But you also have this cluster and this cluster. Now we have another issue. Because how do you measure the distance between the clusters? Do you use this point? Do you use this point? Do you use the middle point? It turns out there's a couple different ways to do it, and it's sort of totally arbitrary which way you do it. So these are called, to distinguish them, to distinguish this business of cluster to cluster distance. This is called linkage, not distance. So cluster to cluster distances, clusters don't inherently have a specific like data value because this is the cluster, but where exactly, like what's the actual XY coordinate you would consider for this to measure the difference? There's different ways to do it. You can use the center, you can use the furthest away points, and so forth. And so there's the different metrics. This is what linkage is all about. Linkage is essentially cluster distance, but not individual point distance is distance, whereas linkage is cluster distance. Okay. To distinguish it. So when we talk about linkage, we're talking about cluster to cluster distance. Again, there's different ways. And these are some of the different ways. I think there's others. Single linkage maximizes the distance between the closest, or minimizes the distance rather. So this right here is a close-up of this cluster and this cluster, the AB cluster and the CD cluster. These are the two closest points. So single linkage would determine these distances, and that would be the distance used. Complete linkage would be the furthest away points. And then there's something called average linkage, which is, I think, what we should use in general. This is probably the best idea is to use this one. You will get, with hierarchical clustering, you will get different results, particularly the further your data actually is away. Like if your data is really, really close, your results probably aren't going to matter. But you will get very different results in hierarchical clustering if you use different linkages. I would not use complete linkage. I have to be honest, I'm not really quite sure what the guidelines are in terms of when to use ones. It seems to me that average linkage would be the most sensible, but there are different linkages. Okay. Then there's something called wards, which I honestly don't understand, but it seems to be a really popular method for calculating linkage. Again, the software will always let you choose which linkage metric. I would say if in doubt, choose average. Or wards, but again, I mean, cluster analysis is highly exploratory, so there's really no like right answer, but you will get different results with hierarchical clustering. These linkage things only apply to hierarchical clustering. K-means clustering doesn't work like this, so this linkage business is something particular to this hierarchical clustering method. Okay. So back to the example. The linkage metric actually for this example turned out it didn't matter. I think I did it with all of them. However, in some cases, you're going to have a hugely different cluster analysis example. So this is back to the example that has now created this cluster and this cluster. So we now essentially have 1, 2. These are clusters, but the individual points are still considered clusters. So now we have like this distance, this distance, this distance, this distance, this distance. So what do we cluster next? Okay. The next step is to find where the next smallest distance is. It turns out the next smallest distance is the distance between this point and this cluster. Okay. And so now this is where the agglomeration comes in. Because now this is sort of joined, this is a cluster, but this is sort of joined on as a part of that cluster, and it's creating an agglomerative cluster that now contains CD endpoint. I think this says F. Okay. Then we keep going. I have to tell the truth. I changed here. I created the colors so that they're all the same because I started with individual points and then I clustered the colors here. Now, the next step would be to cluster this one. You can kind of see that like this is really far away from this, but this is closest to this. So the next thing it gets joined in is this. And we agglomerate that onto that and create this. And then now we have this, and then we have one more cluster, which is to create everything as one big cluster. And now we finish this agglomerative hierarchical clustering. This is not best illustrated with points like this. This is illustrated with something called a dendrogram, or a dendrogram rather. I always get it like wrong, but this is like how it's spelled. And so the dendrogram is a visualization of this hierarchical clustering, and it looks like this. The orange software only does this left to right. It doesn't do it like upside. It doesn't do it like a kind of like tree structure kind of thing. Again, you don't want to confuse these with decision trees anyways. So what are we looking at? We're looking at this right here. This is the dendrogram of this. So A and B are the initial clusters, as are C and D. That was this and then this. Then we join in this guy. And if you look at this, this is the next join in of F. So this right here is illustrating this. Okay. And then we join that with E. And so that is illustrating this right here. And then finally, you can see the AB1. Now finally, this and this right here is where you have the little cluster with the two AB that are still in that bottom left corner, and then the bigger cluster, and now they're joining together. And that's what the dendrogram is doing, is it's illustrating that. They're pretty easy to read once you get the hang of it, but the dendrograms are the visualization of this agglomerative process. So this here is really the same thing as this once you sort of flip back and forth a little bit. Right? Hierarchical clustering is kind of nice in the sense that it's actually very nice in the sense that you can see here in this output, it's lining up like the different, these are the point names. But when you get the output from hierarchical clustering, you might be able to like really easily see like different products all together or something like that. So hierarchical clustering can be kind of, these dendrograms, results of hierarchical clustering can be kind of nice. They can also be kind of like a mess and not really show you much. But again, this is all exploratory, so there's not necessarily a right answer. The axis measures the distance, and by that it means this axis here. So these guys are the closest. These are actually, A and B are actually the closest at 1.4, and then this is like 1 point something or other. These are not the same. The distances I did were not normalized. These are, so they're not exactly the same numbers, but if you did normalize distances, you get the same thing. So this is the intercluster distance that you get. Now, a disadvantage of this technique is honestly, it can be kind of hard to interpret the results. Sometimes, not necessarily. You can actually get like super beautiful results like this. Like this one is actually pretty interpretable. But you can get some just weird stuff. Okay. So that is our first clustering technique, is the hierarchical clustering method. It is, again, very exploratory, and you know, you're working with data that you don't have a structure to, so you're looking for a structure in the data, and this will create possibly some clusters or structures in your data. Okay. It's also, this is kind of like an old days thing as well, but hierarchical clustering, because of the way it computes things, it can kind of be, it can crash your computer. These days it probably won't, but in the old days, like 15 years ago, it was kind of hard to run this. And I actually remember crashing my computer running stuff like this. The other thing is that if you have a really large data set, this one is nice and small, but if you have like, you know, 400 rows, then you're going to get like a really kind of like horrendous output for this. Okay. So there's another way of clustering. Okay. Typically, hierarchical clustering is agglomerative. Typically, you don't do divisive. Divisive would be taking everything all together and then dividing it up. I've actually never seen it done that way, but there is such a thing. An alternative is to create clusters that don't join the entire data set together. So agglomeration, you're taking the data as individual parts and then you're grouping it and grouping it and grouping it. And eventually, at the end of hierarchical clustering, you have grouped together the entire data set. Right? So everything is now all grouped, but it's grouped at different levels where this is the closest ones and then they're next to this, and it's agglomeratively grouped. Okay, and this shows the same thing as that. But there's another method that I actually kind of like a little better, which is the k-means clustering. This one we did do in 101. So if you took 101, you did a little bit of this. This one creates clusters that are basically like bubbles. Okay. K-means is a method for working with unlabeled data again, and k-means is strictly based on mathematical distance. They're both based on mathematical distance. K-means works by setting k, which is the number of clusters. And then what happens is that k becomes random centroids, which are sort of randomly placed. And then the distance from each point to a centroid is computed and computing over again. And then like a minimization occurs, and then each point is assigned to a cluster. Okay. So k-means works with the centroid mean values computed. And then there's new distance computed, data reassigned, and the process repeats again and again. Okay. So let's illustrate this. So here is an unlabeled data set with age and salary. There is no label here. There's no like male, female, rich person, smart person, degree, no degree. There's really no... so the only way to start working with this would be to start doing some clustering, unsupervised learning, because that's what you can do. Okay. So, but when we plot this, so this is the data plotted, and you look at it, you're like, hey, 1, 2, 3. There do appear to be 3 clusters. It does appear that k equals 3 would be a good choice here. But how would you determine this without a scatter plot? You would actually do something that's called a scree plot that I'm not actually doing here. But anyways, hang on, I'm actually going too fast. Whoa, stop. Okay, so there appear to be 3 clusters, so we're going to let k equals 3. If you didn't have the scatter plot, you would do something called a scree plot, and you would actually determine that k equals 3. That's the plot where you look at the elbowing. We did that also for principal components. It's the same plot again. So there appear to be 3 clusters, so watch. I did this in orange, and orange will actually let you do the simulation. It's not under the regular clustering. It's in the like education training part. So you're like, what the heck is this? This is a little complicated to look at first. The dots are the data. This is just the data. And unfortunately, this is not entirely the same plot because this is the regular plot from like just scatter plot, and the other one's from the education version. But you have these points here and this and this. So you have that, and you can see that this is what I'm talking about. This is the data. The squares are the centroids. Okay. Here's what the how the algorithm works. It doesn't matter what software you're using. These boxes are randomly thrown on the screen. If you reran this, you would get these put in different places. So the k-means is these 3 boxes are just randomly put. Like they could be put anywhere. In this case, they were put like this. And so you initialize these 3, quote, random centroids. Okay. And what you do is you determine, it's already color-coded, but this centroid here is closest to this point, and this one's closest to these points. And so that's why they're all color-coded together. But then what you do is you recalculate the distance of the points to the centroid. And when it recalculates, it figures that... I didn't say that right. It recalculates, it figures that of these 4 points, so it kind of like formed this initial group. But then it says, here's these 4 points. Okay. The center of these points is now here. So it's recomputing where the centroid would be. And so now you see the centroids have moved. The data hasn't moved. The actual dots have not moved at all, which is a little hard to see. In this case, the red dot is like underneath the centroid because it's the only one that's there. But so now the centroids, which were randomly placed, you have this stuff here and you have this stuff here. The centroids are recomputed. Now this becomes on top of this because it's just this one. So now the centroids move to their new position in the center of that cluster. Okay. And then you reassign the membership. Because now, if you think about this, these two values here, like they go with the red guy. They shouldn't be with this guy because they're clearly closer to that. So this gets reassigned. Okay. And then they get recalculated. The centers get recalculated again. And now we're almost there. Because now, right, so the reassignment is important because these green guys get reassigned to the red guy, and then the red guy has to move to become the center of the new points. Okay. And so he's recomputed. And now we're almost there. Okay. Reassign membership again. Nothing changes. Now when nothing changes, you're done. Okay. So you can kind of see when I move the slides what's going on. So these are initially, these squares are just randomly assigned. And then the points are assigned to the closest centroid, which was just randomly thrown on the screen. That's what's going on first. Then the centroids are recomputed, which is why they move. So the blue one is the easiest one to see. It moves to that spot. But then when you do that, you now realize that these should be part of the red because they're closer to him. So you reassign the point membership to the centroid. But now these are all like, this is not the centroid anymore, so you have to recalculate it. But then when you get here, it basically stabilizes. There's nothing left to do. And now you have your 3 clusters. That's how k-means clustering works. You determine the number of centroids to put on. They are initially put on randomly. The data points are assigned to the closest one randomly. Then you have this business of recomputing and reassigning. And when you finish recomputing and reassigning, you reach a stable state where the clusters have been determined. It's actually pretty simple. And so when nothing changes, you have stable clusters and you have your 3 k-means clusters. And that's all there is to it. It's really not like super complicated. It's really just a matter of, again, sticking random. You determine there's 3 centroids, you stick them on there. You calculate initially the closest, the points to centroid. And then you recalculate it and move the centroids. And then you do that again, and you keep doing it until you get a stable state, and then you're done creating your clusters. That's the best way to explain it. The biggest problem with this is you have to determine a number of clusters to start with. You have to figure that out somehow, or you can just play with it. But that's a very important factor in in doing cluster analysis. In this case, I can't remember whether I concocted this data or got it from somewhere, but it just worked out like super nice that there are obviously 3 clusters. That will not always be the case. Typically also, by the way, when you do cluster analysis, you're hardly ever going to do more than like maybe 6 or 8 clusters. It's always going to be like, you never do 1 either because that's pointless. You're not clustering anything. You'd always do between like 2 and 8 clusters. So k, even though k is like different numbers, it's not like there's an infinite number of possibilities. Okay. And the example above was kind of obvious because there were the 3 clusters. But what if it isn't? And so if it isn't, you do what's called a scree plot. Okay. These, again, the software does, and we've looked at these before. These are the ones where you take all the variance in the data and reduce dimensionality. It's the same thing. And so this is the same one we looked at before at some point. And so in the scree plot, you look at this, and this is the same as the number of principal components, by the way. 2. So you would choose 2 clusters, and it's really actually the same idea as principal components. The clusters are capturing variability, so you need two clusters to capture most of your data variability. If you think about it, that makes sense because you're separating out the data based on like how variable they are, and it turns out there's 2 groups where there's similarity, and when you do that, you've captured most of the essence of the data. And so the number of clusters is the same as the number of principal components. It's actually the same scree plot and the same idea. Most software will run scree plots, pretty much all of it will. Then there's also this thing called silhouette scores that I just kind of, I don't know if I'd learned about these before or what, but these are little scores that measure how well each data point fits within its cluster. Okay. And so they quantify the cohesion of how close things are within the cluster and separated from neighboring clusters. Okay. And so, we'll look at these when we actually run this. These are they're just little scores and they're calculated like this, where the average distance between the data point is B, and the average distance between data point and all other points is A, and then you do this maximization thing. I've never hand calculated these, so I'm sort of faking it. But silhouette scores range from -1 to 1. So a score of 1 indicates the data point is basically perfectly matched. A score of 0 indicates that the data point is on the boundary between the decision, and a score of -1 indicates you're in the wrong cluster. Okay, so overall silhouette score is the average of the silhouette scores for all data points in the data set, which actually is the important one. And you want to find the overall silhouette score for each value of K. Now, these are actually used to determine K, not like individual data like distances. That doesn't make any sense, I know. Let me show you this. Okay, so this is an alternative to using a scree plot, is what this is. Okay, so one way to determine the number of clusters K is to do a scree plot and look at the elbow. That's the same as principal components. Then there's this other way of using these silhouette scores, which admittingly, I've never like hand calculated silhouette scores. But for silhouette scores, you can get in the software this thing here. And what this is the silhouette score for K equals 2, K equals 3, 4, 5, 6, 7, 8. So for this data, which is our data, I ran it, and I get this little silhouette score calculation output thing. The best silhouette score, the highest one, is the 3. So this is an alternative to doing a scree plot. This scree plot, by the way, this is the old one from the previous. This is not on the data that we're using now, because this is the one from the cheese data. But anyways, so the scree plot output, the silhouette score output tells you that for this data, 3 is a good number of clusters, and you can see that that corresponds to this. 8 would be a terrible number of clusters. 2 would actually not be good either, although 2 I'd imagine would be this one and this one. 4 would probably be like this one, and then like these, I don't know. But 3 is the optimal. The biggest silhouette score is the number of clusters to use. And in orange, this is actually, you can do it either way to determine your number of clusters, but this one's pretty good. Okay. So, that will basically tell you when, and you need that K in order to start. But like I said, if you have to, you can just fiddle with 2 to 8, because realistically, there's only, 1, 2, 3, 4, there's only 7 possibilities for K. Just fiddle with it and look at the clusters. It doesn't take that long to run them. Okay. Or do it formally and look at, K is the best. It should be, and some of you did this. If you took my 101, I remember that when I graded them, everybody did empty cars for this. I don't know what was going on, but some people did it so that they actually looked at like all kinds of different numbers of clusters, which I thought was kind of interesting. But anyways, so that is cluster analysis. Okay. It's not like super duper crazy hard. Again, it's a highly exploratory technique. So when would you want to use K-means and when you want to use hierarchical? I don't know. It depends on you. You can always use both. There's no rule that says you can only do one thing. In data mining, you can use 10 different techniques if you want, which is probably a good thing. See if you get similar results. These are both used for unlabeled data sets. K-means is actually, it computes better. It actually works better with really big data sets. Because again, going back to like this thing, the dendrogram, you don't want a dendrogram with like 900 lines. This, these are cute, but there's like, you can only like handle how many of them fit on like a regular size page or slide, you can't have like bazillions of these. You'll just kind of like go crazy. Or you can kind of like group your data or something, but you don't really know how to group it yet because that's why you're clustering. So anyways, when to use which method, it depends on what you want to do. It depends on what you feel like doing. It also depends on what you know. In general, I would probably go with K-means before I would go with hierarchical. Hierarchical, though, in some cases, you might really want that hierarchical full data set agglomeration. You might want to see how everything's like all joined together. But K-means will give you like nice sort of bubble separation kind of stuff. And that is the theory behind the cluster analysis. Yay! All right. Okay.